I've been implementing a Lisp on Parrot. Lisp was the original dynamic programming language, and Parrot is a VM that aims to support all dynamic programming languages. So it ought to be a good fit. Actually, I first found some areas where it wasn't such a good fit. My Lisp isn't quite a standard Lisp. It actually doesn't have consoles. In my Lisp, the lists are first-class objects, and they're also immutable. And that posed a bit of a problem with Parrot. Parrot has some array types which look like they would be useful for implementing lists, but they're all inherently mutable. So, well, I could have implemented an immutable list type and plugged it into Parrot. That would involve writing a bunch of C code, which I didn't really want to do for a prototype. I wanted to explore Parrot's intrinsic facilities. So what I've done for my prototype is I'm using Parrot's inherently mutable array types as my list, and I'm just not mutating them beyond the initial construction. This means that my list couldn't get along with another high-level language on the same Parrot, because another language seeing the same data would feel free to mutate it, which my Lisp is relying on not happening. But it's good enough for a prototype. So I've got a prototype consisting of about 1900 lines of Parrot assembler and about 400 lines of Lisp. The assembler system in Parrot makes it really easy to get started, but it's in the nature of Lisp that you pretty quickly reach the point where it's easier to extend the system in Lisp than in the original implementation language. So I've got my redeveloped print loop here, so I can show you some simple Lispy computations. Simple addition there. The addition function, it is a function, takes any number of arguments. That's the advantage of the fully parenthesized notation. And I can perform comparisons. That works as you'd expect. I can construct a list. List here is a function that returns a list of its arguments. So that's returned a list. It looks like it's just parroted back what I said. So I can show you that it's a real list object by passing it to another function like that. Or I can run a function borrowed from APL that generates a longer list. And I can show you a simple example of a higher order function with a lambda expression here. That produces a list of squares. So that much all works. Now, those of you who have seen Lisp before will recognize that the way this redeveloped print loop is showing you lists isn't quite the way lists are normally displayed by a redeveloped print loop. I said my Lisp is not quite normal, and the reason for this particular difference is deeply rooted in the story of how Lisp became a dynamic programming language. Lisp was developed in 1958 at MIT by John McCarthy, the AI department. And originally, dynamic programming wasn't on the agenda. The agenda was symbolic computation. This was something new. The intention was symbolic computation as opposed to the numeric computation, which was performed by the only other high-level language existing at the time, Fortran. So the artificial intelligence people were interested in tasks such as symbolic differentiation. If you look at how these two languages would handle differentiation, with Fortran you could write a mathematical formula into the source code of your program, and then you can use Fortran to evaluate that, and by numerical methods you could evaluate its derivative. You could evaluate that at many points and then draw a graph. That's classic numerical computation. But the idea with symbolic computation was you'd be able to put the same mathematical formula into a Lisp program as data, and it would give you back a formula for the derivative. So, that was the intention, symbolic computation. So Lisp had to operate on data, unlike the numbers that Fortran operates on. Lisp was designed to operate on structures of lists and symbols. Originally, there was no compiler for Lisp. The intention was always that there would be a compiler, just like you have Fortran compilers. But originally, Lisp was mainly used on paper. It was used as a paper notation for describing algorithms to operate on symbolic structures. And if you wanted to actually run a Lisp program, which people did, you had to hand compile it into an implementation system, which was done. It's not that difficult to hand compile Lisp programs, but it was taking up too much of the artificial intelligence people's time. So during 1958, they hired a couple of programmers whose sole job was to hand compile the Lisp programs that the artificial intelligence people were writing. And one day in November 1958, one of these programmers was going through a pile of paper programs on McCarthy's desk. He was being systematic about programming more. And he came to a rather interesting program. And he asked McCarthy, should I program this one as well? And McCarthy said, oh, no, you don't understand. This one isn't for computing. This is just for theory. And the program that they were talking about looked something like this. McCarthy was writing a paper not about any of the artificial intelligence tasks that they were interested in, but about the Lisp programming system itself. And he'd come up with this rather interesting construct that he called the universal Lisp function. It's a Lisp function that will take a description of a Lisp expression as a parameter, and it will evaluate whatever that Lisp expression would evaluate. This forms part of the argument around the Church-Turing thesis about the fundamental equivalence of different modes of computation. Theoretically, this has about the same status as a universal Turing machine, which is a Turing machine that will take a description of a Turing machine as input and will compute whatever that Turing machine would compute. But there are some practical differences, starting from the fact that no one actually computes using Turing machines. So the programmer figured that if they actually implemented this universal Lisp function, then they would have a Lisp interpreter. And that would be something radically new. No one had ever had an interpreter for a high-level programming language. And being of a more practical bent than McCarthy, he wasn't dissuaded by McCarthy's statements. He went ahead and hand-compiled this anyway. Sure enough, once they fixed a couple of bugs, they found they did have a Lisp interpreter, and that was the birth of dynamic programming. Pretty soon, this became the preferred way to interact with the Lisp system. It became the way to try out your programs before going toward the effort of compiling it. But it had had some accidental effects on the form of the language. The Lisp notation, as it had been originally devised and was used on paper, had a strict syntactic distinction between code and data. But the purpose of the universal Lisp function is not served by that. For the universal Lisp function, you have to describe Lisp code in the form of the lists and symbols data structures that Lisp could operate on. So soon it became necessary to write code in the form of Lisp data. And that's the syntax that we're familiar with Lisp today. It's what you see on this slide. But it has a profound effect. It means that Lisp syntax does not principally represent code. It principally represents data and only secondarily represents code. In fact, the read-eval print loop, you might possibly not know that the term read-eval print loop comes from Lisp. It's named for the three main functions in the loop. Read is a Lisp function that takes characters from an input stream and constructs a list and symbols data structure from them. eval is this universal Lisp function that interprets data as code and evaluates that to produce a data result. And then print is the opposite of read. It takes a list of symbols data structure and emits it as characters to an output stream. So there's a fundamental asymmetry in the dialogue of the read, eval, print loop. The user is inputting this code, which is encoded as data. But when the computer wants to present a result back, it just prints the object as data with no reference to the syntax of Lisp code. So fundamentally, the user and the computer are speaking different languages. Now, originally, that was perfectly satisfactory, but this data has got more complicated. These days, we're not satisfied with just having two data types and overloading them to mean everything. Nowadays, we like to have a relatively large number of data types and quite purpose-specific data types, and especially we like to have user-defined classes. And gradually, these types have been added to Lisp over the years, and at least in the early days, there was an attempt to maintain the original structure of Lisp syntax principally representing data. But that means every new type needs to have two ways of constructing it. It needs to have some new and increasingly baroque character-based syntax to represent it directly, but it also needs functions to construct it. And over time, this has become an unsatisfactory arrangement. So in my Lisp, I've pretty much reversed that. In my Lisp, the syntax directly represents code, and only secondarily represents data. In fact, in the general case, if you want to represent data in my Lisp, you have to write a piece of code that evaluates to that data. And this means that the user and the computer are now speaking the same language, because the user inputs Lisp code, which will be evaluated to produce some data result, and when the computer wants to describe that data result, it does it by writing a piece of code that will notionally be evaluated in the programmer's head to produce that data result. So we're speaking the same language. And I took this speaking the same language as a guiding principle, and it's had some interesting consequences. So, for my next example, I'm going to give a name to a list. I'm constructing a list in the usual way and then just storing it in the namespace. So it's a list of 3 items. The first item in the list is a truth value, the second is a number, and the third is a function. And if I ask to see that list, it's described back to me in code, actually the same code that I used to input it. Now, I'm going to rename that function that's in the list. I do this just by copying the function value to a new name, and then removing the old name. And if we now look at the list, the computer is now describing that third list element by using the new name for the function. It's kept it up to date. I can give the Lisp printer a more difficult problem than that by removing the name for the truth value. So if I now perform a comparison that will return that truth value, what do I get back? Well, actually, this is not something you can type in. The printer's had to give up. When it finds there's no name for this truth value, it's given up on showing me the exact value. This colon dot syntax means it's something you can't type back in to get the value. It's not showing the exact value, it's just saying the type of the value. And if we look at that list, well, it gives up in the same way, but only for that one list element. The rest of the list is shown just fine. I can restore the name for the truth value. Well, actually, I'm going to restore a different name. And sure enough, the new name is used in both places. But I prefer the name that it had before, so I'll rename that back. The ability to rename things like this goes further. I shall now rename the list construction function And sure enough, when the computer wants to show me code to construct a list, it uses the new name, the list construction function. That all works. So, how is this working? Well, there are a couple of obvious ways in which this could be cleverly done. So, all of these named objects, the functions and the truth value, could internally store a name. And then the printer would use that name. Except it doesn't use that name blindly. Obviously, it would have to check against the current namespace to see if that name is still a current name for that object. And if it's not a currently correct name, then it would have to search the namespace for a new name and store that new name in the object. It could work like that. Or we could put all the cleverness into the namespace object. Alongside the name-to-object mapping, it could also store the reverse object-to-name mapping. And then everything that updates one mapping would have to update the other to match. But actually, you don't need to be clever about this. This object-to-name lookup isn't used as a normal part of computation in this system. It's only used when talking to a human at the read-eval print loop. And so the maximum rate at which you need to perform object-to-name lookups is the rate at which a human can read them. And we puny humans can't keep up with modern computational might. So this system is not clever about this. Every time the printer wants to output a name for an object, it searches the namespace for a current name. So it always produces correct output. It always produces output that is in the same language that the user is currently using for input. It's always correct. So this goes further. I'm going to define a couple of functions here. Oops. I used to be able to type. So that's a function that squares a number. And this is going to be a function that will use the square function to square every number in a list. So I can generate, by that means, the same list of squares that we saw earlier. Next I'm going to look inside the map square function. So I said earlier that the syntax here directly represents code, but obviously as well as that I need a representation of code as data that can be manipulated. So that's done using some purpose-specific objects, which we're about to see here. We don't really want to look at the detail at this stage, but the code objects are being described in the form of constructor expressions. And you can see early on the second line there is a reference to the square function. So what happens now if I rename the square function? If I run map square again now, it still works. And if we look inside it, we see that reference to the square function is now being described using the new name. And I can make this worse by removing the name, the square function entirely. And map square still works. And if we look inside it, instead of getting the name for the square function, that too is now being described in terms of more calls to constructor functions. So, what's going on here? Well, obviously, map square internally, it does not refer to the square function by name, not by the name square, not by any name. It contains a first-class reference to the square function. This has consequences. Suppose I write this function, there is nothing at the moment called will. Traditionally, in a dynamic programming system, I'd be able to enter this function, that would work, and obviously I wouldn't be able to call it. If I call it, there would be an error because Wibble isn't defined. But I would be able to define this and later define Wibble, and then I would be able to call this, and it works. But in this system, it's an error. It's an error to input that code because all the names are resolved to what they're referred to immediately upon input, which poses a problem for a certain class of functions. I have a factorial function which computes the factorial of a number. Now, we'd normally like to define it by some code something like this. But this is a simple recursive definition of factorial function, but it refers to itself by name, which poses a problem. The purpose of writing this code is to define the factorial function. If we don't already have it defined, then it's not valid to input this code, because the name factorial is unbound. So how do we construct a factorial function? You might imagine that that we could construct this function with some dummy reference instead of factorial. And then after building that, we could modify it to contain a reference to itself. But in this Lisp, that's not allowed, because all of these objects making up the function and the code are immutable. So if you want it to contain a reference to the factorial function, you have to start with a reference to the factorial function, which you can't if that's what you're defining. Even if you could construct such a self-referential immutable data structure, there are good theoretical reasons for not doing it. Often when you have immutable data, if you have physically separate objects of the same type, then you want to overlook the fact that they're physically separate and compare them for identity by comparing their content. And you have to do this recursively through all immutable data structures. It stops when you get something immutable, but in order to know that this comparison will always terminate, you need to know that the amount of immutable structure beneath an object will always be finite, which means you can't have such a self-reference like this. That would get you into infinite recursion. And also for mathematical analysis of the system, the main axiomatization of set theory, Zermelo-Fraenkel set theory, has an equivalent rule to this, that you're not allowed to nest sets infinitely deep. So, have I just ruled out recursion? Well, no, I haven't. I've ruled out having a self-referential definition, but I have not ruled out a function calling itself at runtime. Obviously, to call itself, it needs to acquire at runtime a reference to itself. Having that reference built into the definition is merely the simplest way in which it could have acquired such a reference. You can think about other ways that it could be done. It could acquire a reference to itself by calling some other function, for example. It could call the namespace lookup function. It could pass in the string factorial. And let's transform this into looking up the name factorial at runtime. And then we could define that code without having the namespace in any particular state. We could then put it in the namespace under the name factorial, and then call it, and it would manage to get a reference to itself at runtime. Or you can do an equivalent construction using a private variable. But either way, that's not much good for a compiler, because it means that the compiler sees examination of a variable. The namespace is a variable for this purpose. And that means it's difficult for the compiler to prove anything about it. It means it has to allow for that variable to take on any value at runtime. So it can't produce very optimized code. And of course, what happens if you actually put something else in the namespace under the name factorial? It would mean that this function would no longer be computing factorial as we want. So that's not a very good method. there's a third way that it could acquire a reference to itself, which is to have the reference passed in as a parameter, which will look like this. So this is a function that will compute a factorial if you pass in a function that can compute a factorial. Is this useful? Actually it is, because this function does a useful amount of work. It performs one iteration of the factorial function, and it only defers to the function you passed in to do the rest of the job. And at this point we can borrow a trick from lambda calculus. If we pass it through a fixed point combinator, then we get out a complete factorial function. And it looks like this. And in principle, this works. I say in principle because when I actually tried it on Parrot, I ran into a fantastic bug. So, in Parrot, obviously the functions that I'm defining are of a user-defined class as far as Parrot is concerned. But they're also called. Parrot defines a way for you to define the behavior of a user-defined callable object. Basically, you have a method, you provide a function that's attached to the class, and that function will get called with, as arguments, the called object and the arguments that were passed to the called object. Okay, that much works, but internally, to implement the call to that, Parrot has a bit of logic to construct that argument list. That it starts out with the argument list that was passed to the called object and unshifts the called object onto the list, except that it first looks at the argument list to see whether the called object is already there. And if it is, then it doesn't unshift it. So all of my calls to list-defined functions had been working perfectly well until I started passing a callable function to itself as an argument, which happens in the middle of the fixed point combinator. And at that point, it lost that argument from that call, and it all fell over. And this was a devastating bug. All the other bits of Parrot that I'd run into trouble with, I could work around or avoid. I found the class system to be unusably broken, so my Lisp at the moment basically doesn't have a class system. But this one I couldn't work around. Passing objects freely to themselves as functions, yes, that has to work. So I had to actually go into Parrot and fix it. This was the only bit of C code that I wrote to make this prototype work. So anyway, once that bug is fixed, this works and produces a complete factorial function. Obviously it would be a bit cumbersome if we had to write that every time we wanted to write a recursive function. But this is Lisp. We've got macros. In fact, there are already some macros there. The colon syntax indicates a macro. Colon if and colon fn are macros. So we just wrap all of that up as a new macro, and it looks like this. And that looks almost normal. Yeah, so given that, we can attribute lots of factorials. Because this is all big number arithmetic, we can compute some rather large factorials. There's no real limit to how large a factorial we can compute here. Except when there is. So this is another Parrot feature. If you list your function calls 1,000 levels deep, then it says maximum recursion depth exceeded. What is this recursion limit? Well, it's not documented. I'm not sure quite what it's trying to achieve. It looks a little as though it's trying to stop you running out of memory before you get there. But the limit doesn't depend on the amount of memory you've got. Whether you've got a megabyte or a terabyte, the limit is 1,000 levels deep. It also doesn't stop you using as much memory as you want if you do it iteratively, or if you disguise your recursion as tail calling by using explicit continuation parsing. As far as I can tell, It's just training wheels. It's for novice programmers to stop them getting confused by recursion. Fortunately, the limit is settable. And now we can compute large factorials.